Subject of this video is going to be graphs of trigonometric functions. Now, an important distinction between trigonometric ratios and trigonometric functions is going to be the idea of what are we now inputting and what are we now outputting. For reference, we're going to pull in the unit circle. If I were to tell you that there is an angle in standard position, and we'll refer to that angle as theta, normally we would be able to see something like the cosine of theta is equal to x, and the sine of theta is equal to y, and be able to base everything off of that. Typically, though, when it comes to trigonometric functions, x's and y's tend to be our inputs and our outputs, respectively. So when we say trigonometric functions, we are going to get into the following mindset, where x is now going to be referring to your angle, and y is now going to be referring to your ratio, whatever it happens to be. So with that in mind, we have 6 different trigonometric functions, which means that we're going to have 6 different trigonometric ratios that we're dealing with in the form of these functions. Now we're going to cover the first 2 of them today, and that's going to be the sine and the cosine. So we are going to once again be expanding the library of functions. And the 2 that we're going to add today, we're going to bring in y equals the sine of x, as well as y equals the cosine of x. So in both of these cases, x is referring to your angle, and y is referring to the corresponding ratio, regardless of whether it's the sine or the cosine of that angle. Now, when it comes to the library of functions, there are a number of things that we are supposed to know. Those things are the general shape of the curve, 5 points on the curve, whether or not it has symmetry, along with its domain and range. From one of our previous videos, we were able to come up with several of those properties. Now, we are going to start with a slightly abridged version of the sine function. What we're going to do is define this thing in terms of one full rotation on the unit circle. That's where the angle is going to go from 0 to 2 pi. So first thing we'll do is copy down some points. Now, when it comes to the points that I'd like you to use here, we usually talk about 5 points. I would like to use our quadrantal angles. These 5 would be our quadrantal angles. We'll be calculating the sine of each of these. Now on the unit circle, given an angle, the sine is going to be the y-coordinate of that angle. So when the angle is 0, the sine of 0 would be the y-coordinate at 0. At pi over 2, the angle in question would be this guy up here. The y-coordinate at that angle is 1. At pi, the y-coordinate at pi would be 0. At 3 pi over 2, we'd be talking about this point down here. The y-coordinate at this point is -1. And back to 2 pi, that's coterminal to 0, so I would expect to see the exact same thing. So we'll mark these 4 x values along the x-axis. Here's pi over 2, pi, 3 pi over 2, and 2 pi. So go all the way down to -1, all the way up to +1. I'm going to plot these 5 points, and like the majority of the functions that we've been dealing with throughout the course of the semester, there are 2 words that we use to describe something like this, and they are smooth and continuous. So the smooth continuous function that passes through these 5 points will look like this. Now, if we wanted to expand this in both directions, then as long as you have it passing through the origin and starting off by increasing, you can essentially copy and paste this thing over and over, and you would get the graph of the entirety of y equals the sine of x. Oh boy, okay. So maximum values are going to be at +1, minimum values are going to be at -1. This shape will repeat itself over and over and over and over again. In fact, it will repeat indefinitely. Now, as far as the other 3 things that we tend to look for, the domain is going to be all real numbers, since it does repeat indefinitely. The range is going to be from -1 to +1. You'll notice that if we were to turn this graph upside down, we would be looking at the same graph. So this is an odd function with origin symmetry. Now there are some other aspects of the graph that we're going to take a look at. So other aspects of the graph. We'll call this other important stuff. There are a whole lot of x-intercepts on this graph. The first one occurs at x equals 0, and then we get x equals pi, and then 2 pi, and 3 pi, and 4 pi, and so forth and so on. In fact, this will have an infinite number of x-intercepts, as it will strike the x-axis an infinite number of times. So the way that we express 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, etc. is we simply say k pi, where k represents any integer. Additionally, this thing will attain a maximum value an infinite number of times. The maximum value that it hits is a y-coordinate of 1. The first time that it hits that maximum value is at x equals pi over 2, and then it will repeat that every time it makes a full revolution around the unit circle. So that'll be plus 2k pi. Additionally, it attains a minimum value an infinite number of times, and that minimum value is -1. The first time that it attains a value of -1 is at the angle of 3 pi over 2, and it will repeat that every 2 pi units. So again, full rotations on the unit circle. So corresponding to the unit circle, the maximum value would be up here, and corresponding to the, oh boy, probably shouldn't have made that axis first. Pertaining to the minimum value, that would be right down here, occurring at 3 pi over 2, and every full rotation of the unit circle beyond that. Cool. So we'll commit that one to memory. The other one that we'd like to introduce is y equals the cosine of x, and once again we'll start on the interval of 0 to 2 pi. So the corresponding points that I'd like to use will be the same as before. I'd like to use angles of 0, pi over 2, pi, 3 pi over 2, and 2 pi. Now for each of these angles, we'd be interested in finding the corresponding x-coordinate, as that is consistent with the cosine. So from the unit circle, angle of 0 would be here. The x-coordinate at that point would be 1. Pi over 2, that would be up here. The x-coordinate at this point would be 0. At pi, x-coordinate would be -1. At 3 pi over 2, the x-coordinate would be 0. And back to 2 pi, the x-coordinate would be +1. The graph is going to look very similar to the graph of the sine function, just staggered a bit. So we'll see points here, 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 and here, where the x scale is pi over 2. So once again, smooth and continuous are going to be the names of the game. Now if we wanted to copy and paste this a whole bunch of times, so that it extends infinitely in both directions, you would wind up getting a graph that looks kind of like this. So the sine passed through the origin, the cosine did not. That will repeat indefinitely. Maximum value of 1, minimum value of -1. So this would be the more complete graph of y equals the cosine of x. Now with those things in mind, we see that this does extend infinitely in both directions, so the domain will be all real numbers. The range will be from -1 to +1. And I do see that there are corresponding points directly through the y-axis. So this would be considered an even function. So even function with y-axis symmetry. Some other important stuff to know. Like the sine function, this will have an infinite number of x-intercepts. The first x-intercept is going to occur at x equals pi over 2, and will repeat every pi units after that. So once again, k is going to represent any integer. As far as the maximum value is concerned, this occurs for the first time at 0 and will occur every 2 pi units after that. The maximum value attained is 1. The minimum value attained is -1, and this will occur for the first time at x equals pi and repeat every 2 pi units thereafter. So these two things would be our mother functions, and we will be talking about transformations after this. In both of these cases, for both the sine as well as the cosine, the shape of the graph is referred to as sinusoidal. The suffix oid meaning looks kind of like that thing, and the prefix sine meaning, well, it looks kind of like a sine function, which makes a lot of sense because, well, one of them is a sine function and the other one looks just like it.